So, big welcome to Ciprian Manolescu, who's going to tell us what he's going to talk about.
Oh, okay. Shit.
Everybody mute themselves before they swear, please.
Sorry.
All right, ready?
Yep.
So, yes, so I will be talking about, first of all, thank you for inviting me to speak. I will be talking about Hovanov homology and the search for exotic force spheres. Okay, so it always does this. Okay, here we go. All right, so the main motivation for the talk is this famous conjecture, the smooth Poincare conjecture in dimension 4, which I'm going to refer to as CPC4, which says that if a smooth 4 manifold is homotopy equivalent to S4, then it's diffeomorphic to S4. And what we know from Friedman's work is that homotopy equivalent implies homeomorphic. So this is equivalent to asking about the existence of exotic smooth structures on the force sphere. Okay, so unlike with many other conjectures in math, we don't even have a good idea if this should be true or false. So I think opinions are split on whether we should expect this to be true. In fact, over time, many potential counterexamples have been proposed. So these are manifolds that are homeomorphic to S4, but not known to be diffeomorphic to it. And in many cases, other people later shown them to be standard, to be diffeomorphic, but then other people came up with new examples and the game goes on. So based on the history, maybe you could think it's true, or maybe you could think it's false. Let me just say that we don't have too many ideas for how to prove it. So instead, more people have been focusing on showing that it's false, just because there are some suggestions of how to do that. And that's what I'm going to talk about today. So here is the one strategy for this proof, which is an old strategy. I think people thought about it back in the 80s, but it was revived recently. So the idea is to find a knot that's not sliced, meaning that it doesn't bound a smooth disk in the 4 ball, but K bounds a smooth disk in some homotopy ball. So that would imply that the homotopy ball is exotic, it's not B4. And if you add a standard ball to it, you would get a non-trivial homotopy force sphere. So to implement this strategy, you need two things. You need, first of all, a good source of examples of homotopy 4 balls. And that's basically the same as homotopy force spheres. You take out a ball out of a force sphere and you get a homotopy 4 ball. And you also need some construction of knots that bound disks in these balls, in these homotopy balls. And secondly, you need a knot invariant that would tell you that K is not sliced. So this should be something that, say, vanishes for sliced knots, but does not necessarily vanish when the knot bounds something in a homotopy ball. So you have to be careful with that. And the main candidate is the Rasmussen's invariant called S. I will review what it is. So there was a paper by Friedman, Gumpf, Morrison, and Walker more than 10 years ago, where they proposed using the S invariant, and they actually showed a homotopy force sphere. It was a Capel-Shainson sphere, and they found a knot that bounds a disk, and they computed the S invariant, and it turned out to be 0, so it didn't work. And in fact, the homotopy force sphere itself turned out to be standard, as was proved by Agbolut almost immediately afterwards. But still, there's this strategy, so maybe we could try it for other things. So there are lots of slice invariants. There's things like the Fox-Milnor condition or signature and so on. But those don't distinguish between sliceness in B4 and in a homotopy 4 ball. And neither do gauge theoretic invariants, like there's invariants coming from instantons or Hegardt-Fleur. Yeah, basically don't see this difference. So the S, we don't know. I mean, it might still be insensitive to this, but there's no proof of that. Maybe also, maybe a decade ago, Kronheimer and Brovka put up a paper where they claim that S also obstructs bounding disks in homotopy balls, so it vanishes when that's the case, and then it wouldn't help for this strategy. But then they later retracted the proof. It had a mistake. So maybe that made people not think about this for a while, but now that they retracted the proof and S might still work, we can think about it again. Okay, so here's what I'll do in this talk. First, I'll review a little bit about Hovanov homology and Rasmussen's invariant. Secondly, I will talk about basically 3 results that are related to this strategy. First, why it fails for Gluck twists. That's the first result. Second is why it's like the analog works to detect exotic smooth structures on other 4 manifolds, so not on S4. And finally, a new attempt to pursue this strategy using some construction of homotopy spheres from zero surgery homeomorphisms. So these are joint work with several collaborators. The first one with Marengon, Sharkar, and Willis, the second with Marengon and Piccirillo, and the third with Piccirillo. Okay, so let's review Hovanov homology. This is a bi-graded theory for knots, and its definition, I'm sure many of you have seen it many times, but let's just have it, involves doing taking the resolutions of link diagram, all possible resolutions. You put them in a cube, in a hypercube. In this case, it's a square for the Hopf link. And then to each circle, you associate this 2-dimensional vector space V. You take the tensor products at for each resolution over all the circles, and you get some complex like this. Yeah, with some shifts in gradings. I'm not going to talk about the gradings. And then the differential D has to do with whether, I mean, it's just defined algebraically depending on whether we glue 2 circles together or we split a circle into 2. And there are just some formulas. So if I let V be the span of 1 and X, we have this multiplication map on V, which corresponds to circles getting joined together. And if we split it, we have a co-multiplication map. So there are some formulas, and using this, you get this chain complex, and the homology is Hovanov homology. So here are some properties. Its Euler characteristic is the Jones polynomial. And what will be very important for us is that it's sort of functorial under cobordisms. So if you have a cobordism in S3 times 0, 1 between 2 knots, a surface, you get a map on Hovanov homology. To be honest, the map is only well defined up to signs, but there are ways of fixing the sign discrepancy if you want by giving a slightly different definition of Hovanov homology. All right, so it has something to do with surfaces in some particular 4 manifold in S3 times 0, 1. So that gives us some hope that it actually can say something about 4-dimensional properties of knots and surfaces. Okay, so why does it do this? Yes, okay. So the Rasmussen invariant is constructed from a deformation of Hovanov homology. So you can add, you can change the differential a little bit by adding some terms, and then you get a simpler theory, the Lie homology, which, for example, for knots is just Q plus Q, and it lives in homological degree 0 and quantum degree differing by 2. So S minus 1 and S plus 1. And S is this Rasmussen invariant. So basically you get a spectral sequence to Q plus Q, and you look at where the Q live in what grading, and that's the definition of Rasmussen's invariant. So the spectral sequence also behaves well with respect to cobordisms. If you have a cobordism, you get a map of spectral sequences. So that allowed Rasmussen to say something about surfaces with boundary or not. So he showed that S over 2 is a lower bound for the slice genus of the knot. The slice genus is the minimal genus of a surface in B4 with boundary the knot. So it's important that the surface is in B4, not in a homotopy ball, because we only know, from B4, you can take out a ball and get S3 times 0, 1. And we only showed functoriality in S3 times 0, 1. That's where we know what to do with Khovanov homology, basically because Khovanov homology is defined from a planar projection, and you can think about how to change what happens with cobordisms in that. But if you're in a homotopy ball, you don't know if you have the same kind of maps. So that's what gives us some hope that maybe it distinguishes balls, homotopy 4 balls from the standard ball. Okay, so in particular, yes, if GS is 0, so if there is a disk with boundary K, meaning K is slice, then this inequality tells us that S equals 0. So here's a standard picture of a slice knot bounding a disk in B4, where the 4th dimension is the color. Okay, so so one other thing that gives us hope is that Khovanov homology by now has some good topological applications in 4 dimensions. In particular, it has been used to reprove theorems that were previously accessible only with gauge theory or Hegardt-Floer homology. And the first famous example of this was the Milnor conjecture, which calculates the slice genus of torus knots. So it says that the slice genus of TPQ is P minus 1 times Q minus 1 over 2. So this was proved using gauge theory, namely the Yang-Mills equations. It was proved by Kronheimer and Brovka in 1993. And then Rasmussen, as an application of his invariant, he gave a new proof, which is completely combinatorial, in 2004. One consequence of Rasmussen's work was the existence of exotic smooth structures on R4. So this can be obtained as an application of the existence of topologically sliced knots that are not smoothly sliced by work of, I think it first appeared maybe in a paper of Gumpf, but where he cited Casson as having this idea. So you can use Rasmussen's invariant to find some topologically sliced knot, so something with Alexander polynomial 1, like a Whitehead double, and then you compute the S invariant and you get that it's non-zero, and therefore the knot is not slice. And then from here, there's some topological construction that gives you exotic R4. Okay, so these two were about surfaces in B4 and structures on R4, which are pretty simple for manifolds. But then there's also, more recently, the Thom conjecture, which was also proved by Kronheimer and Brovka in 1994 with gauge theory, now has a new proof by Lambert-Cole in 2018. He used Khovanov homology, and he showed this conjecture, which is about surfaces in CP2. So he showed, so the conjecture said that the minimal genus of a surface in the class D times the generator in CP2 is D minus 1 times D minus 2 over 2. So that's kind of interesting because we only know about how Khovanov homology behaves in S3 times 0, 1, but so Lambert-Cole uses that plus some trisection theory and also contact geometry, and somehow he reduces it to that case. So he can say something about CP2. And then more recently, he also has a paper, so Lambert-Cole from 2020, in which he proves the general adjunction inequality in symplectic manifolds. So this is some inequality about the genus of a surface in a certain homology class in a symplectic manifold. And this gives, for example, the symplectic Thumb conjecture, which was proved by Horschbach-Szabo originally, and says that symplectic surfaces in symplectic 4 manifolds are genus minimizing in their homology class. And the consequence of this is the existence of exotic smooth structures on some closed 4 manifolds. So this was also known using gauge theory, and now there is a proof using Hovanov homology. Okay, so these were all the results, but reproved using these combinatorial methods. There are also some new results. For example, Lisa Piccirillo in 2018 showed that the zero shake genus of a knot can be different from its slice genus. So I won't get into the details, but okay, the zero shake genus is you look at the trace of zero surgery on a knot, which is a 4 manifold with boundary, and you look at the generator in homology, and you look at what's the minimal genus of a surface representing that. And before people didn't know if this was different from the slice genus, and she gave some examples, and the proof used the Rasmussen invariant. And more famously, she also proved in a different paper that Conway's knot is not slice. So this was a knot for which a lot of invariants, slice invariants vanish, including S, but she managed to find some other knot that has S non-zero, and from the non-sliceness of that knot, she deduced the non-sliceness of Conway's knot. So these two new results, the only proofs we know are based on Rasmussen invariant. Like we don't have any proofs with gauge theory. Of course, on the other hand, there are also many gauge theoretic results. For example, Donaldson's original diagonal visibility theorem for 4 manifolds. Those we don't know how to prove yet with Hovanov homology. But this raises the question, to what extent can Hovanov homology say something about 4 manifolds that gauge theory didn't? So, I mean, Piccirillo's results were sort of about 4 manifolds, were about knots and surfaces that they bound in some simple 4 manifolds. But what about actual, like saying something about closed 4 manifolds? And okay, so one thing you could try is to use Hovanov homology to get invariants of 4 manifolds, like gauge theory was used to give Seiberg-Witten an instanton. And there is a proposal for this. I wanted to mention this just in passing. So Morrison, Walker, and Wedrich, proposed a candidate. The simplest version of that is called the Skene-Lasagna algebra. And that's an invariant of knots in the boundary of a 4 manifold. And it depends on the 4 manifold. It extends Hovanov homology, but it's very hard to compute. So I wrote a paper with my student Nate Talat, and where we computed it for CP2 and disk bundles over S2. So for simple examples, and it's open whether this can actually detect exotic smooth structures on 4 manifolds. Like, I think maybe yes. I mean, it has the potential to do so. I don't see why not. But at the same time, it's very hard to compute. So I don't know if this is out of reach. Well, it's out of reach at the moment, but we'll see what happens. So I won't talk about that. But I'll talk, so what I wanted to talk about today mostly is this Friedman, Gumpf, Morrison, Walker strategy for disproving the SPC4, which is to use the Rasmussen invariant. So we want to find a knot with S non-zero, so hence not slice, but bounding a disk in a homotopy 4 ball. Okay, so here's something interesting. Now, in principle, you could win either way. So either Kovanov homology has the same properties as Seiberg-Witten or instanton theory or Hegardt-Fleur, which means that it's functorial for 4-dimensional cobordisms. And then maybe if it has like exactly the same properties, then it wouldn't be able to distinguish between homotopy 4 balls and regular 4 balls. So the strategy would fail for SPC4. But on the other hand, if we had this, then we would get like 4-manifold invariant. So maybe we could say something about smooth closed 4 manifolds, like the K3 surface or something like that. So that would be good in some sense. Or maybe it doesn't have the same properties. Maybe there's something specific about S3 times 0, 1 as opposed to something else. And then we would have a chance of disproving SPC4. So in principle, yeah, either way, there is some hope. Okay, yeah, so now I'll get to talking about these 3 results about the FGMW strategy. Okay, so the first one is about Gluck twists, which are a popular way of constructing homotopy for spheres. So Gluck's construction starts with 2 knot, which is an embedded 2-sphere in S4. You look at a neighborhood of it, and then you remove it and glue it back. So, but yeah, so you take S4 minus N union N, using this self-diffeomorphism of S1 times S2, the Dane twist, basically. And you can calculate the fundamental group and the homology of this manifold, and you get that they're the same as S4. From here, you deduce that it's a homotopy 4-sphere and therefore homeomorphic to S4. And the question is if it's diffeomorphic to S4. So this is not known in general, although it's known for many families of 2 knots. So once in a while, people write papers that, that for these families of 2 knots, the Gluck twists are standard. Okay, and a few years ago, there was even a paper claiming that all Gluck twists are Stanford, but again, it was retracted. So it's still not known in general. Okay, so our result is that if, so this is work with Marengon, Sharkar, and Willis from 2019. If K bounds a smooth disk in a homotopy 4 ball obtained from B4 by a Gluck twist, then S is 0. So S cannot tell between knots that bound disks in this kind of homotopy balls and knots that just bound disks in the ordinary 4 ball. So therefore, this strategy, that FGMW strategy, it fails for Gluck twists. Right, so this is sort of a negative result. Okay, how do we prove this? Okay, so the key thing that I'll say a few words about it in on the next slides is that if K bounds a null homologous disk in CP2 minus B4, so we look at CP2 and either take out a ball or take connected sum with a ball, those are the same thing. You look at the knot in the boundary of that, which is S3, and you look at, see if it bounds a disk in there, a null homologous disk. Then we prove that S has this inequality, S is greater or equal than 0. And the mirror version of this is that if it bounds such a disk in CP2 bar minus B4, then S is less or equal than 0. Now, what does CP2 and CP2 bar have to do with Gluck twist? Well, there is a well-known result that if you start with B4 and do a Gluck twist, then whenever you add CP2 or CP2 bar, you get something standard. So you get B4 plus CP2 or B4 plus CP2 bar. So the non-triviality of the Gluck twists definitely disappear once you stabilize by either CP2 or CP2 bar. This is something you can prove with Kirby calculus or just by studying the local model around the 2 knot and what happens when you add this a sphere of self-intersection plus or minus 1. Okay, so if you know this, then let's see. So let's prove the theorem sort of. We have K, it bounds this disk in the Glock twist in Z. And then, well, let's just add a CP2. It would still bound a null homologous disk in that, but that's CP2 plus B4, and there we know that S is greater or equal than 0. And similarly, we know S is less or equal than 0, and therefore S equals 0. Okay, so the key thing that we need to prove is something about how S behaves for disks in CP2 bar, or equivalently CP2. So let's do the CP2 bar. We want to show S is less or equal than 0. So how did we prove this? Well, in principle, we only know about Kovanov homology and S3 times 0, 1, cobordisms in S3 times 0, 1. But we can reduce to that case. So if you look at S2 at the core, the CP1 in CP2 bar, which is this blue circle I drew here, and you remove it, then you get exactly S3 times 0, 1. So if you have your knot, and let's say it bounds some surface, then that intersects S2 in a number of points. And what you get a cobordism between K and something that just depends on how many points you intersected S2 with. And that something turns out to be a torus link. So it's T2P2P, this FP. And because this is null homologous, it needs to have the same positive and negative number, the same number of positive and negative points in the intersection with S2. So yeah, so it's going to be T2P2P with P arcs oriented one way and P oriented the other way. Okay, so then we just look at S3 times 0, 1, and there, well, then we can apply what Rasmussen proved and was generalized by Belyakova and Verley. They show that you get this inequality between the genus of the surface or the Euler characteristic, Sk and SFP. So you have a cobordism from K to Fp of some genus. And once you compute the S invariant of Fp itself, of this torus link, which you can do, I mean, that's the technical part of the paper. You have to use some Hochschild homology. Then you conclude that when you have a disk, when the cobordism is a disk, you get that S is less or equal than 0 from this inequality. So once again, you just use the properties of Kovanov homology and the Lie deformation in S3 times 0, 1. What you need is the S invariant of this torus link. Okay, so we get something in CP2 bar. Let me make actually a definition. I should have done this before maybe, but let's just do it now. Let's say that a knot is H slice in a 4 manifold if it bounds a null homologous disk in X minus B4. So when you take out a little ball and you put the knot on the boundary on S3, if it bounds a null homologous, if it just bounds a disk, we say it's slice in X. If it bounds a null homologous disk, we say it's H slice in X. So what we showed is that if K is H slice in CP2 bar, then S is less or equal than 0. And you can apply this to the mirror, and you get if it's H slice in CP2, then S is greater or equal than 0. And then from here, you deduce the thing about Glock twists. Now, for future reference, because I will come back to this, let me also mention that we could generalize this to H slice in a connected sum of CP2s, or if you want a connected sum of CP2 bars. So if it's H slice in any connected sum of CP2s, we still have S greater or equal than 0. Okay, so that's all I'll say about these Glock twists. The strategy fails for them. Now let's do a more positive result. So the FGMW strategy is about using the S invariant to hopefully say that the set of H slice knots would detect an exotic smooth structure on S4. Well, at some point we started thinking, I mean, can the set of H slice knots detect exotic smooth structures on other 4 manifolds. I mean, other 4 manifolds are better understood than S4. And it turns out to be true. So what I proved with Marangon and Piccirillo is that there exist closed, smooth, homeomorphic 4 manifolds, X and X prime, and a knot that is H slice in X, but not in X prime. So therefore, X and X prime are not diffeomorphic. And this is our example. A K is the right-handed trefoil, and these are the manifolds. So one is some connect sum of CP2s and CP2 bars, and the other is the K3 surface blown up ones, so plus CP2 bar. So I should say these were known to be diffeomorphic before. I mean, you can do it with gauge theory. But what the theorem says is that the set of H slice knots detects these exotic smooth structures, this exotic smooth structure. So you can see it by just looking at which knots are H slice in one, but not in the other. And I should mention this has nothing to do with Khovanov homology. So we're using gauge theory. We're using the Seiberg-Witten equations in the proof. But it's still, this gives us some hope that maybe the set of H slice knots is a good thing to look at to detect exotic smooth structures. Okay, so let me sketch the proof of these results. So these are our manifolds, X and X prime. The first observation is they're simply connected. They have the same intersection form. You can compute it. And Friedman's theorem implies that they are homeomorphic. Okay, then we need to do some explicit topological constructions. So first, you can show that the trefoil bounds a null homologous disk in CP2 minus B4. That's not hard to see, but let me not go into it. But once you have that it bounds a disk in CP2 minus B4, then just add some, they connected sum with something. Observe that CP2 is part of X. It's not part of X prime, but it's part of X. So if you found a disk in CP2, then just when you take connect sums, it's still there. So you get that that K is H slice in X. It bounds a disk in X, a null homologous disk. And on the other hand, okay, so the other thing we need is you can, like just starting from the Kirby diagram of the K3 surface, you can find a disk in the K3 surface with boundary K bar, so the left-handed trefoil, and the disk is not quite null homologous. So its homology class is non-zero, but the square of the class is 0. Okay, so now we still need to show that K is not H slice in X prime. Well, if K were bounding such a disk in X prime minus B4, then we want to put it together with this other delta that we already found, and we get a sphere. We would get an embedded sphere in K3 plus X prime, which is K3 plus CP2 bar. And yeah, so this sphere would be something null homologous plus this delta. So overall, it would still satisfy that the homology class is non-trivial, but its square is 0. So you would get a sphere in such a class. And there's a theorem of Intushel and Stern that that's impossible when the Seiberg-Witten equations have non-trivial solutions for any metric. So their theorem was about when the Seiberg-Witten invariants are 0. In this case, the are non-zero. Sorry. In this case, the Seiberg-Witten invariants are 0, but you can use some refinement, a stable homotopy refinement due to Bauer and Furuta. That is non-zero for this manifold. Yeah. The main thing is that it's basically a connected sum of 2 symplectic manifolds or 3 symplectic manifolds. And you show that, yeah, that having such a sphere is not possible. So using some gauge theory, and therefore K is not H slice in X prime. Okay, so that's the proof of the second result. Again, it says that the set of H slice knots can detect exotic smooth structures. So because K is H slice in one of these, but not in the other, it means that they are not diffeomorphic. Okay, so for the rest of the talk, I will focus on the third result. I mean, the third kind of attempt at pursuing the FGMW strategy, which is what I've been doing with Lisa Piccirillo. It's a work in progress. I mean, we're almost done. I hope the paper will come out next week. Okay, so before I talk about that, let me introduce some definitions. Given a knot, we can construct a four-manifold XK, which is called the trace of K, and it's obtained by attaching a two-handle to B4 along K. So you look at K in the boundary, and you attach this two-handle, and you get some four-manifold with boundary. And that I'm going to call the trace. And the boundary is the zero surgery on K. That's not hard to see. The boundary is this three-manifold, which is alternatively is obtained by taking out a neighborhood of K and putting back the solid torus using this gluing that reverses the meridian and the longitude. Okay, so the zero surgery has the homology of S1 times S2. All right, so we have the trace and the zero surgery, and here's how we can, here's a new way of constructing homotopy. I mean, it's not new. People knew about it. It's a new, how should I say? It's a new way of attempting the strategy using another construction of homotopy four spheres based on zero surgery homeomorphisms. So let's say we have two knots and their zero surgeries are homeomorphic or equivalently diffeomorphic. I mean, we're in dimension 3 when we talk about surgeries, so homeomorphism and diffeomorphism are the same. Okay, so if you have this, then let's also suppose that one of the knots is sliced. So it bounds a disk in B4. Then we can look at the complement of that disk, of a neighborhood of that disk. So let's call that V. So it turns out this also has boundary, the zero surgery on K. So you can glue to it the trace on the other knot. Maybe let's note, if you glue together the trace on the same knot, let's look at the picture. So if K bounded the disk in B4, then you would, then you would split B4 into two parts, B4 union the disk, which is the trace, and the rest would be the complement of the disk. So together they would be S4. But here I'm gluing together, instead of gluing XK, I'm gluing XK prime, of course, with the opposite orientation to make it work. So then what you get is not necessarily S4, but you can show it's a homotopy sphere, four sphere. Right, so if I have this homeomorphism and one of the knots is sliced, I get a homotopy four sphere. And furthermore, K prime naturally bounds a disk, right? So what we need is a source of homotopy four spheres and also knots that bound disks in them in W minus B4. And it does bound the disk. I mean, if you look at the picture, if I have a knot, then it bounds, by construction, it bounds a disk in the trace. If I take out a ball, from the trace, it bounds this disk in the trace. So similarly here, I just glued the trace of XK prime to something, but by construction, K prime is going to bound the disk in W minus B4. So this gives me a homotopy sphere and knot that is H slice in it. So if we could find an example such that K prime is not slice, so by using Rasmussen's invariant, so S is non-zero, then we would disprove SPC4. Yeah, because K prime would bound a disk in a homotopy 4 ball, but not in the ordinary 4 ball. So what we need again is the zero surgery homeomorphism. One of the knots should be sliced and the other not sliced. Now, a caveat is that we want to avoid a case when phi extends to a trace diffeomorphism. So we want a diffeomorphism between the zero surgeries, but not one between the traces. That would be too much to ask, because then the sphere would be standard. So let me talk just a little bit about trace diffeomorphisms. So these are useful for some purposes. There is this trace embedding lemma, which says that a knot is slice if and only if its trace embeds in B4. This is not hard to prove, it's a lemma. And this was what was used by Piccirillo to show that Conway's knot is not slice. So she found a knot C prime with the same trace. And then because of the trace embedding lemma, one of them is slice if and only if the other is slice. Because the sliceness can be expressed in terms of trace, of the trace. And then she showed that C prime is not slice by computing the S invariant, and therefore C is not slice. So it's good for these purposes to find like knots with the same traces, but that's not what we want for our strategy, right? So if we had the same trace, if K and K prime had the same trace, then more precisely, if the homeomorphism of the surgeries would extend to the traces, when we add xk prime to V, it would be the same as adding xk. And this just gives the standard S4, so not an exotic one. Okay, so we need some knots with the same surgeries, the same zero surgeries, and there are various constructions in the literature, like dualizable patterns and annulus twisting and some satellites. In many cases, these produce knots with the same traces, so that's not useful to us. In some cases, they don't, so that could be useful, and we looked at some of these constructions. But in the end, we just gave a general construction of all zero surgery homeomorphisms. So it turns out you can express all of them in terms of some three components links, which we call RBG links. So red, blue, and green are the colors of the three components. Okay, so how does this work? So an RBG link is a rationally framed link with three components. So you have some three rational numbers RBG, such that when you do surgery on R and G, you get S3, and when you do surgery on R and B, you also get S3. And you also want H1 of surgery on everything to be Z. That's all you need. Oh, yes, question. Are they notorious? Hopefully they will be after this talk. Yes, this is the notorious RBG links. Okay, so here's a theorem. It's not a hard theorem. I'll explain the proof really quickly. So to any RBG link, you have a pair of you can associate some knots, KB and KG, with a zero surgery homeomorphism. So having the same zero surgery. And conversely, for every zero surgery homeomorphism, there's an associated RBG link that produces these knots. These are many-to-one correspondence. So for every zero surgery homeomorphism, there are actually many RBG links producing these knots. So so the way it works is, okay, it takes a minute to think about it, but it's almost a topology. So given the link, you let KB be the image of the B under under this psi B, and G to be the image of G under the second homeomorphism. And then it turns out that the zero surgery on them are the same as the surgery on the whole link. That's all. And conversely, if you have phi, you let the blue knot be K prime, and you let the red knot be the image of the meridian for K under the given homeomorphism phi, and you let G be the framed meridian for R, the zero framed meridian for R. And it turns out this is an RBG link that gives KB and KG. So it's just, yeah, it's just rephrasing the zero surgery for homeomorphism in terms of these links. But the interesting thing is that it's easy to construct many, many such links. So here's like how, like one of the easiest way to do it is to find links like this we call special RBG, that such that if you look at just R and B by itself, B looks like the meridian for R. And if you just look at R and G by themselves, G looks like the meridian for R. And there's some condition on the linking number and the framing. But let me just show you an example. So here blue is the meridian for red. And then if you ignore blue, then you can untwist these things in the green, and you also end up with green as being the meridian for R. Okay, so yeah, and maybe I should say, so how do you get the KB and KG knots from this? You have to slide G over R to remove the linking between B and G. So if I look at this other picture, you see that G intersects the blue disk, the disk bounded by blue, in 2 points. And I want to do some slides to remove those intersections. And that would give me the knot KG. And similarly, we get KB. And yeah, and then this will tell us that we have these 2 knots with the same zero surgery. So here's the picture. Yeah, so I do some slides of green over red, and I end up with this KG knot, sorry, KG knot, the green knot. Or equivalently, I can make the green one to be the R knot, and then I handle slide, I slide the blue over red, and I end up with another knot. So our theorem says that these have the same zero surgery. All right, so this gives us a lot of examples, and let's just recall our goal. We want an example where one of the knots is sliced and the other has S non-zero. Okay, and if we had that, we would get an exotic force sphere. Okay, so let's look at the big family of knots. We just feed it into the computer. We looked at a family with 6 parameters where we're just including more and more full twists on these 6 locations in the link. And this still is a special RBG link, no matter how many full twists you have. So we let these parameters go between -1 and 1 or -2 and 2. And we looked at this family and we computed things. These are the knots that come out of the family, the blue and the green. Okay. And okay, so all right. So we didn't find any bona fide examples where one of them is sliced and S is non-zero. Otherwise, this would be a different talk. But still, we found some interesting stuff. We found examples. So first of all, there are many examples where one of the knots is sliced. But then the other has S equals 0. So the companion, in some cases, we know it's sliced. In other cases, we don't know. But in any case, you can construct a homotopy force sphere if one of them is sliced. You just don't know if it's exotic. And the S invariant doesn't help. But that's still some homotopy force spheres. And more interestingly, we also found examples where when one of them is S is non-zero, and the other one, we couldn't tell if it's sliced or not. So it might be sliced. And why we couldn't tell is because all the sliceness obstructions that we could compute vanish. So these 21 examples, they satisfy Fox-Milnor, and in fact, they're algebraically sliced. And yeah, and then other slice invariants, like not just the Rasmussen invariant, but also other variants from Kovanov homology over other fields or from the Steenrod squares on Kovanov homology due to Lipschitz-Sharkar, they all vanish, and also the slice invariants from Notfler homology vanish. So everything we could compute vanishes. And in fact, 5 of these 21 examples are topologically sliced. They have Alexander equals 1. Oh yeah, and the other way we could show that people show that things are not sliced are the Piccirillo way to find, if there was a trace diffeomorphism, then this wouldn't work. but we could show for at least 12 of them that the homeomorphism doesn't extend to the traces. And maybe it doesn't extend for the others as well. So these are, and then we also try to show that they're slice, but we try to find like ribbon bands and we couldn't find them. So yeah, so I'm just, I want to leave this kind of as a question. Are the following 21 not sliced? So if you find that one of them is sliced, then you disprove the SPC4. And here are the examples. So here are the first 3 knots. Here are some more knots, more knots, more knots. That's it, 21 of them. The simplest one is K17. K17 has 16 crossings. So they range it between like 16 and 40 crossings. Okay, so, all right, so let me just review what the point of this is. So these are examples where S is non-zero for the companion, for something that has the same zero surgery, and then we don't know if K is sliced. And if it were sliced, then we would disprove SPC4. So let me also mention, yeah, there's a slightly less ambitious goal, but still ambitious. If you think disproving SPC4 is a crazy idea, maybe you could try to find exotic structures on the connected sum of n CP2s. Now, this is also an open problem. It follows from the work of Friedman and Donaldson that these are the only simply connected 4 manifolds with definite intersection form. Let's say positive definite would be NCP2 and negative definite would be NCP2 bar up to homeomorphism. But it's open whether they have exotic smooth structures. So if they're diffeomorphic to NCP2. So you could, okay, so the same strategy in principle could work for showing this. So let's recall one of the results that I mentioned before. If K is H slice in NCP2, then S is greater or equal than 0. So if we found a pair of knots, K and K prime with the same zero surgery, and H was S slice in one of them, then we could hope to prove that that the other one is not H slice in NCP2 by if it had S less than 0. And this would give us an exotic smooth, an exotic structure on NCP2. All right, so, well, okay, why does this sound a little easier than SPC4? It's, I mean, knots that are H slice in NCP2 are more frequent than just slice. So you can find such knots if you just have, if you have a sequence of n crossing changes from positive to negative that make K into the on knot. Then from here, you get, I mean, a crossing change is a cobordism in CP2. So you would get from here that it's, the knot is H slice in NCP2. And in fact, there are many BPH slice knots. So these are the ones, I mean, we introduced this term. It stands for biprojectively H slice. It means that it bounds null homologous disks in both NCP2 and NCP2 bar for some n. So if it's like this, then it has the signature equals 0 and S equals 0, just like for slice knots. So in a sense, this is a generalization of slice knots, but it's a much more frequent generalization. So for example, if you look at the simplest knots, the ones with up to 9 crossings that have signature 0, those also have S equals 0. And only 7 of them are slice, but we could show that almost all of them are BPH slice. So all except possibly one. For one of them, we couldn't show if it's BPH slice or not. For 819, I think, or one of, yeah, something with 8 crossings. Yeah, so BPH slice knots are more frequent. And the 21 knots in our list, well, what did they have? So they had S equals 0 and the signature was 0. We couldn't tell if they're slice. And their companions had S equals -2. So maybe showing that its slice is hard. If you could just show that there H slice in NCP2. Oh, as a remark, we can show it's not hard that there are H slice in 3 copies of CP2 bar. If you could also show that there are H slice in NCP2 and hence BPH slice, then you would find an exotic NCP2. Okay, so yeah, so maybe showing that their slice is hard, but maybe they're at least BPH slice. Of course, they may be neither. That's a perfectly valid guess. I don't know. Let me mention that we found 2 other candidates for BPH sliceness. So they're kind of like our other examples, but they don't satisfy Fox-Milnor on the Alexander polynomial. So we know that they're not sliced. They won't produce exotic S4s, but their companions still have S equals -2. So if you could show that they're H slice in NCP2, you would still get an exotic NCP2, which would still be very good. So these are the last 2 knots that are candidates for BPH sliceness. All right, so this is all I had to say. Thank you.
Thank you very much, Ciprian. Are there any questions? You'll have to unmute yourself if you have a question.
Just a bibliographic question. Piccarello's result on the Conway knot is listed as 2018. Wasn't it published more recently?
Yes, but I'm using the years from the archive.
Oh, that's what she found. Great, great.
You know, you can't blame people if it takes a long time to be refereed.
Yeah. Is this called experimental knot theory or not quite?
Yes, I mean, yeah, I mean, a lot of our paper is just, I mean, half of it is developing these RBG links, and then half of it is just computer experimentation.
And the computers can go wild with this, right? I mean,
yeah, so we just looked at one family.
Yeah.
But you can find some other families. I guess I should say our family is general enough. So the knots you get from this are genus, cipher genus at most 2 and slice genus at most 1. And you can, like, if you look at the list of small knots, I don't know, up to 10 crossings with these 2 properties, then almost all of them are part of this family. So it's quite general. But of course, you can take some other RBG links and just compute and see if you get lucky. At this point, we tried for 1 year and we're ready to just put the paper out there and let other people try to. There was a question in, oh yeah, can it be proved that those 21 knots are not ribbon knots? No. I know there are some ribbon obstructions that are not known to be slice obstructions. We didn't compute it. I mean, I think they're pretty hard to compute, so we didn't really try. But yeah, we don't know if they're ribbon.
Are there any more questions from anybody? Well, I think we could just thank Ciprian for a very interesting talk, which is obviously going somewhere, but we'll no doubt find out in the future. So thanks again, Ciprian.
Thank you.
Thank you very much.
Okay.
And be sure to send us a copy of your slides.
Yeah.
Yes, I will.
And I will send round a copy of the recording of this talk, and also give some more details about future talks next week and so on. So thank you. I'll stop now.